Hello, we're going to have a look at 3 uses of hashing algorithms, which I think you need to know about to be able to understand hashing and the sort of things which in an exam you'd be expected to know. So this is important because hashing is weird. It's a one-way function. It's not immediately obvious why we would want that. Why would you want something where you cannot reverse it? But there are uses for it, which we'll go through. The most common one, which everybody must know, is passwords. So this is the go-to example of where hashing is used because it's a perfect use for it. So passwords should never be stored as the original password. If you are writing a program which takes in passwords and stores them in a file, you need to make sure they're being stored as hash values. So if I'm setting a username and a password, the username I may hash, I may not. The passwords we definitely should store as hash values. And the person should have a database table which has, let's say the usernames are not being hashed, they're just stored normally. Compsci123 shouldn't appear in this table. What should appear is the hashed version. So I run a hashing algorithm, I get this scrambled output, and that is what gets added to my database table. The reason why I would do this is because if somebody stumbles upon this list of passwords, you get hacked or someone finds it in your source code, well, if it's in the original version, their passwords have been exposed. Whereas if a hashed password gets exposed, it shouldn't really be a big deal because ultimately you can't reverse it, you can't go back to the original, and you also can't use it. So you should be fairly safe storing the hashed value. And despite it being impossible for anybody to reverse it, we are able to use the hashed passwords to authenticate somebody, to tell if somebody is who they say they are. This is only possible if our algorithm is deterministic and collision resistant. I'll say more why in a second. But let's say later on, I go and log in. How does the program know I am the correct person? Well, I put in my username, I put in my password. It will have to calculate the hashed version of this password. It needs to be deterministic so that I get the same hashed value as earlier. If it wasn't deterministic, it might be a different value, in which case I'm now locked out of my account. So it needs to be consistent. It will then check that username in my database and compare the hashed password it has with the new hashed password. If they are equal, then that must mean I am the correct person. I only can trust this if I believe my algorithm to be collision resistant. If it's possible there are collisions, then I might get really lucky and type in a wrong password, but it lets me in because it happened to be a collision with the correct password. That's very unlikely, but is a possibility unless it is collision resistant. And because we should get a unique output with no collisions, if I was to type in a wrong password, I type in computing exclamation mark, well, that gives me a completely different hash to compsci123. So therefore it can quickly tell I've typed in the wrong password and it won't let me in. Now, hashing doesn't solve all issues related to passwords. For example, it doesn't prevent brute forcing of the input. I could try every single possible combination, and after a huge amount of combinations, I would eventually end up getting the correct hash value and it would let me in. Now, the longer the password, the more this becomes effectively impossible, but you could do this. This is why password programs will lock you out after 5 incorrect attempts or something like that to prevent this brute forcing. A slightly cleverer version of this is when an attacker pre-computes hashes of common passwords. So before they come across a leaked database or whatever, they will sit, or they won't, but a program will sit and calculate hashes of loads of common passwords. Maybe millions, maybe billions of these, in the hope that one day they come across a leaked database which contains the hashed passwords of all of these users. Well, these passwords in hashed form are not reversible. I can't reverse it. But what I can do if I've got a long list of possible hashed values is see whether any of these hashes in my table match up to my pre-computed database. Well, in this case here, we can see this bottom hash matches Guido123's hashed password. And assuming it's a deterministic algorithm, therefore Guido123's password is stupidly password. So this is a way of reverse engineering a hash without actually breaking the hashing itself. We're just using brute forcing in a slightly cleverer way. Now, we can not solve this completely, but help this by not just hashing the password alone, but including a sort in this process. So a sort is a random value which can be combined with your regular input. So I put this random value alongside my regular input, and this will give me a whole different hashed value. And so therefore, the attacker doing all this hard work to calculate or pre-compute these values is now rendered meaningless because they can't predict my random value. Therefore, their hashed version is different to mine. Now, we would need to store this sort alongside the table. So an attacker could still brute force if they knew the sort, but it means they can't pre-compute it, which is often the most sensible way to do this. So that is an example of where sorts are used to try and cut down on predictability. Another use of hashing is within anti-malware software, which is there to detect malware on your computer and remove it if it finds it. And it's for detection, which is where hashing is useful. So if I'm a company who have anti-malware software, the first step is to try and find some malware. I then hash this malware and store these hash values in a database. So my company right now has discovered 2 bits of malware in the wild. I've hashed these and I store these hash values in a database. I then go out and find a new bit of malware. I go on a dodgy website and try and deliberately get some malware. It's brand new. I hash it. And when I say I hash it, I mean I'm hashing its code, which will be a machine code. So I'm hashing for machine code, which is binary. It produces a hashed value. I then stick this in my database. I might find that actually this is already in the database because it's actually been discovered already. But if I get a new hash value, I've discovered a new bit of malware. I add it to my database. And this is all at the company's end. In terms of our users, well, the user have the anti-malware software installed on their computer. This database can be included within that anti-malware software. This is safe for a user to have. It's safe in the sense that a user can't get a virus or ransomware or whatever from a hash. It's also safe in the sense that you're not giving a wannabe attacker all the different malware because they can't reverse it. So this is not reversible. Therefore, I can't just get this malware if I wanted to. And this database being on your computer is useful because when the anti-malware software detects a new program, it will hash this new program and compare it to the database. So I've downloaded a new bit of software, looks okay to me, but the anti-malware software will run the hashing algorithm, get the hash, compare it to the database. This hash isn't in the database, therefore we can hope this is valid software, which is not malware. With a different one, I might hash it. Actually, it, despite looking okay, is in my database. Therefore, I know I've got malware. Therefore, it can try and delete it. Now, this isn't a perfect process. If you got brand new malware, which the company hadn't discovered, not much you can do about it. If you haven't updated your database recently, you're more likely to get new malware, which you won't be able to detect. And also, this is an example of where having the avalanche effect actually is maybe not super desirable, because the avalanche effect is where a tiny change in the input has a big effect on the output. Well, if I'm an attacker, I might just every day add a new print line to my malware because it will completely change the output of the hash. So that would bypass this method. Whereas if I just added some print lines and slightly modified it and it didn't have the avalanche effect, then the hash would still be different, but it might be a little bit similar to the previous one. And you could use some algorithm to determine how similar this hash is to a known malware's hash. So avalanche effect is useful in lots of cases, good with passwords, not so good with anti-malware potentially. To give you a third and final example of hashing being used in communication, it can also be used to help check for errors when data is being sent over a network. We don't use hashing to send data for security reasons because it can't be reversed. We use encryption for securely sending data. We can use hashing to check for errors when data is being sent. So if I want to make sure my message doesn't have any errors, I'm going to hash this message before it gets sent. If I'm sending hello, I'm going to hash it. I will then include this hash in the packet I'm sending. So a data packet will contain a header. The header will contain things like the IP addresses and the protocol being used and the sequence number, but it will also tell the computer what hashing has been used. And this hash value is also called a checksum. So in this context, this value is called a checksum. So the checksum is being created using SHA-3. I put my message in the body of the packet, and in the trailer of the packet, I put this hash, I put this checksum, which matched up to what I did earlier. I then send this packet. and it goes to whoever I'm sending it to. When this packet arrives, the hash will get recalculated. And if it's different, there must have been an error in transit. So how does this work in practice? Well, my packet has arrived. Here it is. I'm now the receiving device. Well, I can only see this packet. I know it's used SHA-3. I can see the message is yellow, and I can see the hash value here. I'm going to recalculate the hash using SHA-3. So I find the hash of yellow using SHA-3, which is this. But hang on, this hash is different to this hash. So therefore, there must have been some error in transit. Obviously, H and Y have got swapped somehow. Errors happen all the time over networks. This is how I can tell an error has occurred. If it's really important, I can then request the person sending it resends it, and it will repeat until eventually the hashes match up so that I know it's been sent correctly.